We started talking about naming with polyatomic ions, and that's where we're going to continue. And again, this you do need to know. I'm not making you memorize things that are not important to memorize, but this is important that you know it. It'll be much quicker if you know how everything works and you have these memorized. So you have to know these. I'm never going to be a chemistry teacher that says memorize the periodic table. That's silly. But you do need to memorize these. So we're naming, bless you, our compound by naming our cation first and naming our anion. And in most cases, our anion is a polyatomic. Of course, ammonium is the only positively charged polyatomic ion on this chart. In organic chemistry, any compound could be polyatomic, meaning a compound with an overall charge. But these are our most common ones that we see that interact with salts. So those are the ones we're going to memorize. So I left you with naming the polyatomic ion FeNO3. So first thing I want you to note is that the NO3 is in parentheses with a 3 subscript. This says that we have 3 NO3 ions that are interacting with our iron cation, with one iron cation. So when you have multiple polyatomic ions in our empirical formula, you have to put it in parentheses. You don't just want to put a 3 associated with the oxygen. It's different. The NO3, that is the way that our ion is always connected. And if any numbers on the nitrogen or oxygen change, it's no longer that ion. Because those are covalent bonds that have an overall charged molecule. So that's why we have to put it in parentheses. If it's only 1, then we don't show the 1, so we don't have to put it in parentheses. But we have to make sure if there's multiple of that polyatomic ion, the whole polyatomic ion is in parentheses, and then the subscript shows how many of that ion we have. So that's really important to know. Also, iron is a variable charge, so we need to figure out what charge that ion is, and we can do that by balancing, because we know that our ion, our Fe ion, cation, and our 3 NO3 anions have to cancel out and have a net charge of 0. So the first thing we're going to do is identify our ion. Our NO3 ion must be NO3 minus. Our iron, in that case, must be 3 plus. Looking here, we have our NO3 minus. And that's our only, we don't have a polyatomic ion with another charge for NO3. So we know it has to be minus. So we have to memorize that nitrate. And of course we need to memorize the name because that'll be important when we're naming. So that means that our iron must be 3 plus for that to balance. We have 3 NO3 minus, so we must have 1 Fe3 plus. So our overall balance charge will be 3 plus 3 minus. So now we can name our cation, and remember, since it's variable, we have to put the charge of it in parentheses in Roman numerals. So this will be iron 3. That's our metal, and we have to show that 3. And then naming our anion, again, from the table, we know that this is our NO3 minus, so that's nitrate. So our anion is nitrate. And then we just put this together, iron 3 nitrate. It is not necessary to capitalize the iron. If you were using that in a sentence where it was the first word, you would capitalize it, but it's not necessary to have it capitalized. It's not like your name, which would always be capitalized. So that's just a side note. You're going to have multiple choice, clearly. And do pay attention to your online homework. If it specifies that the first letter should be capitalized, make sure you do that. Otherwise, it'll tell you it's wrong. Usually, it'll say in the corner how they want you to put your answers in. But in general, if I were just asking you to write it in a blank, I wouldn't care if it was capitalized or not. That's just a side note. Writing papers and things like that, it doesn't have to be capitalized, unless if it's starting a sentence. So if we look at this one, I'll start it again, even though technically you answered it last time. So of course, this is nitrate. If it was copper 2 bless you. If it was copper 2 nitrile, then it would just be the nitrogen. But since this is nitrate, this is our polyatomic ion. So this is another reason why you need to know those names and what those root names mean. So between A and B, the difference is balancing. This specifically tells us we have copper 2, so that means we have a 2 plus charge. And our NO3 has a -1. So the correct answer is B. Oops. To balance that. And remember, we must put this in parentheses if it is a polyatomic ion. Very important. The next naming we're going to talk about is hydrates. Hydrates are ionic compounds containing a specific number of water molecules for every formula unit. There are a lot of compounds, a lot of ionic compounds that are strongly interacting with water through intermolecular forces, which we'll talk about later. I don't really like the order of the book, because the order of the book, we learn all these things, and then in chapter 7 and 8, we learn why it's true. I don't like that. I'd rather just do it all at once. But so those of you in 113 can stick with the lab and learn things as you're learning. I'm going to stick with the book order. But we're going to learn what causes some ionic compounds to really tightly bond with water. But those hydrates, those ionic compounds that interact with water strongly, and it's not a covalent bond necessarily, it's not an ionic bond necessarily, they just have a strong affinity towards water. They attract water a lot. And we utilize those all the time to our advantage. They're called hydrates. And we can remove the hydrate by heating them, and then the water evaporates off, and we're left with our solid compound. And we'll often use these types of, we'll call them anhydrous when we don't have any water. And we'll use these types of compounds to dry organic solvents, remove water from organic solvents. We might take a tube and stuff it with this, and then pass a gas through it to dry the gas. So, example, air, your atmosphere air, especially here, depending on the day, pretty humid. We have a lot of water in it. Let's say water affects our reactions, so we don't want to do it under an atmosphere that has water. So we might use an inert gas like nitrogen and pass nitrogen through a drying tube containing these anhydrous compounds that interact with water, and it'll pull the water off. And oftentimes they'll change colors when they do this, so it's really nice. And I'll show you a picture of that in a second. So we have to have a way to name these. And I believe in lab you do a little bit with the hydrates. So for example, this cobalt chloride, typically, because of the way this molecule bonds, and we're not really going to be predicting how many waters are going to interact right now, that's not what you're going to be responsible for, but typically 6 water molecules will interact with one molecule, well, not really molecule, with our lowest empirical formula of Cl2. So we need a way to name them. So the way we name hydrides is pretty easy. In the name, we're going to attach our waters, and then we're going to show that indicated by the term hydrate. And the amount of waters, we're going to use a prefix. You do need to memorize these prefixes. The nice thing is, most of these prefixes will go over to organic chemistry with you, so you'll be using them often. So hydrate just represents the water, and then the prefix represents how many moles of the water, whatever this number is. So for example, this number is 6, so our prefix is hexa. So this would be a hexahydrate. Most of these aren't very hard to memorize. You already know mono means 1. That's not new. Di means 2, tri means 3, tetra means 4. Again, not new. Penta means 5. You've heard of pentagrams. You know it's a 5. You've been in geometry. A lot of these are coming from geometry. Hexa, hepta. Hexa and hepta are the biggest ones I find students mix up. Hexa is 6. Hexa, hepta is 7. So 7 has that P. Remember, 6 has an X in it. So hexa, you can kind of remember that. The X's. most people know others. Now, you can get more of these and you can have a larger hydrate, but these are the ones you're responsible for up until the 8. So you just put that with the name. So, for example, this is cobalt 2 chloride. We know it's 2 because chloride is 1 minus, based on where it is in the periodic table. Cobalt is a variant charge, so we must specify that too. And then we just put hexahydrate on the end. So we're just putting the hydrate on the end. Just like when we draw it, we just put a little dot in the water on the end. So very similar. Now you can have a half a molecule of water. It's not really true. You don't really have a half a molecule of water. You're just making the empirical formula of whatever our ionic compound is. So what that means is one water molecule is interacting with 2 of our ionic molecules. That's all it is a ratio. So to keep our empirical formula all whole numbers in our formula, we just put that as a half, even though you can't really have half a water molecule. So it's just like, I wouldn't be half a person if I'm touching both of these students. But if we did a ratio, you can say that they're 1 to 1 half. So that's kind of what you're thinking of. So for that, it's hemi. Hemi means 1 half. So that's that particular ratio. And again, notice SO4. We don't have a molecule. That's an S and an O, so this must be a polyatomic ion. So that would be calcium sulfate. And then we just add this hemihydrate. So as soon as you see water, then it's a hydrate and you specify it that way. Like I said, oftentimes the hydrate or the anhydrous where there's an absence of water, oftentimes you see a color change. So again, not all the time. Sometimes there's no color change. But in this case of cobalt, the different amount of electrons surrounding cobalt can change the color that we see visibly. And we see a change when we're in the hydrate form and the anhydrous form when you heat it up and remove all the water. So like I said, if you're starting with blue and you're passing, let's say, a gas through it to remove the water, it will no longer remove water once it turns pink. So you can follow that color change to see what you're doing. Here's another example. I'm not sure exactly which one this is, but this one, bless you, is white when it's dry and blue when it's attached to water. So we use a lot of those in the lab. If we're looking at this example, what is the formula of magnesium sulfate heptahydrate? So first off, we have magnesium. That's pretty easy. It's magnesium. So we know that's Mg. And then that's also with our sulfate, which is SO4 2-. That is the polyatomic ion that goes with the name sulfate. So the first thing we want to do is balance this. That is a 2+ charge and a 2- charge, so it's going to be MgSO4. That's balanced, it already cancels out. Next, we want to attach our water. Hepta means 7, and as soon as you see hydrate, it's H2O. And then you just put a dot. And that just means it's associated. Again, this isn't a covalent or ionic bond. This is just an attraction. And we'll get into more of that later on in the semester and how these are actually interacting with our salts. But right now, you just need to be responsible for the name. If we look at this one, we have nickel. Nickel is variable, so we need to know what ion we have. And then we have a hydrate. So first off, chlorine is 1-. We have 2 chlorines for every 1 nickel, so we must have a nickel 2+. So we need to specify that in the name where we have our 2 in our parentheses. That's really important. Then we have a 6. So that is a hexa. Again, a good way to remember it. 6 has an X in the name, so it has an X in our prefix. So it's a hexahydrate. So it's nickel 2 chloride hexahydrate. And that's 3 separate words. Well, technically nickel 2 chloride, you don't need a space, but you do put a space between the hexahydrate. The next thing we're going to talk about, well, let's just put in together our names. Oh, our covalent bonds. we're going to learn how to name really simple molecules that contain covalent bonds that only have two binary molecules, so two elements that are interacting with each other. Organic chemistry, you're going to learn a whole new naming system. Those can have multiple atoms bonded together, things like acetic acid, things like that. But we're going to just name the simple ones in here. We're not going to get into organic chemistry naming. So these are fairly straightforward when we have two atoms that are bonded through a covalent bond, or two different elements. They might have multiple amounts of those elements. So we write our name of the first element in the formula, and we put the one that's the first element, the one that's the most metallic. So the element that's closer to the metals. If we're comparing hydrogen and oxygen, hydrogen looks more like a metal, so it would be first. If we're comparing nitrogen and oxygen, nitrogen is closer to the metal, so it would be first. So you put the more metallic first. And we use the full name of that element. And then the second element, we change the N to I. Like we were naming an ion, but we're not actually forming an ion. There's a reason for this. It has to do with what we call electronegativity and polarity in our bond. And we'll learn more about that later on again. There's a reason why we name it as an I. But it doesn't actually contain a full charge. It doesn't contain an ion. Then we need to specify the amount of those elements that we have in the molecule. So we specify those with prefixes. With the exception of mono, we never use mono for these. We don't like to specify one in chemistry. So otherwise we'll be using, so we don't use mono on the first element. We can use mono on the second element. We don't use mono on the first element. Why? I don't know. But that's the way that it's done. So that's how we learned it. And we just learned those prefixes, so we don't have to learn new prefixes. Except I am giving you two more, which is nano and deca for 9 and 10. So you do need to know up to 10 for those prefixes. But it's all the same prefixes that we talked about before. Now you won't have a hemi with these. You won't have a half. Because what we're talking about is molecular bonds, actual covalent bonds. So we won't have half an element. Because these are actually all bonded together. If the actual name of the element begins with a vowel, just drop the 8. So let's look at an example. We have BF3. So our first element is boron. That's it, just boron. Our second element is our fluorine, but we're going to change it to fluoride. Then we're going to add our prefixes. Boron is more metallic. It is closer to the metals in the periodic table. So we're also going to draw that first in the name. So it's going to be boron, and we don't have a prefix because it's only one of them. So therefore, we don't say anything. And then our fluorine, we have 3, so it's trifluoride. We drop the mono from the first element, so it's boron trifluoride. And we do show a space between those two. If we look at dinitrogen pentoxide, we have nitrogen, and oxide would be oxygen. So those are our two, nitrogen, and oxide would be oxygen. Then we have our amounts, because unlike with covalent bonding where we can use the charge from the periodic table, that's not how it's not how covalent bonding works. It's how ionic bonding works. So you need to know the ratio of the elements from the name. You can't just look at nitrogen and oxygen and decide. Because nitrogen can bond to oxygen in different ways. Carbon can bond to oxygen for different ways. That's how we have carbon monoxide and carbon dioxide. So you need to know that from the name. You can't just guess it from the periodic table. Once you've been in chemistry for a little while, you get bonding patterns that you know and understand where they come from. So you know that it's really unlikely that carbon would bond to 5 oxygens. Not unlikely, it's not going to happen because of the way that carbon bonds. But right now you just are using the name. So we know we have 2 nitrogens because we have di, and we know we have 5 oxygens because we have pent. So That tells us 2 and 5. And also notice that A was dropped because oxygen starts with a vowel. So it's not pentaoxide, it's pentoxide. So what we have is N2O5. And we still draw these with, when we're talking about having only 2 elements in our molecule, we draw our most metallic over. So looking at these, this one's incorrect because we have 2 phosphorus atoms and we're not specifying that. We need to specify that. If I drew this from the name, I'd have PO5, and that's not true. It's P2O5, so I would need diphosphorus pentoxide. Dihydrogen monoxide is in fact correct for H2O. We don't name our ionic bond, and this is an ionic. We have a sodium ion and an NO3 ion, so that's an ionic bond, and we don't name that with our mono. We don't I don't think there's anything wrong with dipotassium monoxide. That one should be red as well. Oh, that's so silly. That's an ionic bond. We don't name those that way. It's potassium. So even though that might be KTO, we wouldn't put the di because this is an ionic bond. And here again, we have an ionic bond. And it's not balanced correctly. Because remember, our oxygen is 2 minus. So if we have 2 irons, that wouldn't balance. That would be a +4 and a -6. That's not balanced. So this must be a +3. The next thing we're going to name is our acids. Acids or molecular compounds, well, our Bronsted-Lowry acids are molecular compounds that dissolve in water and dissociate in H+ ion. There are other types of acids that don't form an H+ ion, but that's beyond what we're talking about right now. But as far as naming, when we're talking about naming acids, these are going to have a hydrogen that's going to form an H+ in water. We call that dissociating H+. So to indicate that the compound is dissolved in water, we put aqueous by it in the name after our formula. Aqueous just means water. If it's not dissolved in water, it's not typically named as an acid. So we're usually understood that there's water present. Oftentimes acids taste sour. Think about your vinegar. Though vinegar is a molecular acid, so it won't be named the same way that we're talking about here. They dissolve many metals. Acid will dissolve your zinc, iron, and magnesium, but not gold or silver or platinum. So you actually, if you take a copper penny and put it in acid, the copper pennies that have zinc on the inside, because they don't all have copper, the inside will actually dissolve after a certain amount of time, where the copper will be left. So it's pretty cool. Generally, our acids that dissolve in water to form H+, they're going to have a hydrogen somewhere, and they generally start with hydrogen. For example, HCl, H2SO4. So the naming isn't very difficult, but there's a couple of rules you need to know as far as naming. Ooh, it's cold. So let's talk about our rules for naming acids. There's 2 main categories of our acids that have hydrogen in the formula. Those are our binary acids. They contain only 2 elements. They have an H+ cation and some sort of non-metal anion. So those make sense, and that naming is going to be pretty straightforward. Then we have our oxy acids that contain oxygen typically they have an H plus cation and a polyatomic anion. Now in reality, when there's no water present, the H in whatever it's bonded to is a covalent bond. But in the presence of water, we're going to form H plus cation and our anion that results. So we typically name it like it's an anion, because when it's dissolved, that's what it forms. And when you get to acids in 106, you're going to learn a bit about dissociation and things like that, and how they're usually in equilibrium. But for naming, we're just going to stick with this for now. So for binary acids, it's pretty straightforward. We're going to write the hydro prefix for the H, followed by your nonmetal name, but instead of the ending, we're going to change, instead of I, it's going to be IC. And then you write acid at the end. You have to include the word acid. So for example, HCl is hydrochloric acid. So our anion is our chlorine, because it's in group 7. And then we're just going to change chlorine or chloride to IC. So hydrochloric acid is how we're going to name it. So binary acid's pretty straightforward to name. The oxyacids can get a bit more, it's not really difficult to name, you just have to know some rules. So if the polyatomic ion name ends in 8, then we change the ending to IC. However, if the polyatomic ion name ends in ite, then we change it to OUS. So that tells us what polyatomic ion we're using. And then, of course, we write acid at the end of the name. So, for example, H2SO4 is our ion, SO4 2-, that's sulfate. So it's 8, so we're going to change it to IC. So it is sulfuric acid. Notice we do not put the hydro, because we can't have hydrosulfic acid. We can also have sulfuric acid. The hydro means it would be HS, H2S. And this means it's the polyatomic ion. So notice for the polyatomic oxyacids, we don't put the hydro. It still might end in IT, it might end in OUS, but we're not putting the hydro for the polyatomic ions. So let's look at H2SO3. Our ion is SO3 2-, so that's our sulfite. Ite will change to OUS, so it's sulfurous. It sounds really good to put sulfus, so we put that UR. There's not really a lot of rules for that necessarily, but it's usually written in the way that it sounds better, so hence sulfurous and not sulfus. So, yeah. So notice the UR from sulfur is kept. Then we have to put acid at the end, sulfurous acid. So we know if we see sulfurous acid that we started with the ite. So looking at this one, H2CrO4, again, what we're looking at is a polyatomic ion. So we have CrO4. That's our CrO4 2-, that's our chromate. So that's going to be chromic acid. And again, we don't put the hydro in front of the name when it is a polyatomic ion. Only when it's a binary acid do we put the hydro first. So like I said, it's not real difficult. You just have to do some practice and learn the rules, and then it's pretty easy to name. But you do have to spend a little bit of time with the rules. Now, if we are starting with the formula, or if we're starting with the name, when a name ends in acid, we know we're going to start with a hydrogen. So, we write the formula as if it's ionic, balancing the hydrogens to balance out our charge, even though, unless if it's dissolved in water, it's actually a covalent bond. But if it's dissolved in water, we form our ion, so we do the same thing. Remember, if you see hydro, you just have a binary acid. But if there's no hydro prefix, then it's an oxyacid. So for the oxyacid, if you end in IC, you know you started with a polyatomic ion that starts in 8. And if it ends in us, you know you started with the ite. Sorry, I'll fix that. So for example, hydrosulfuric acid. Notice it finishes in IC, but I know that my ion is sulfur and not my polyatomic ion because I'm starting with hydro. So sometimes it won't matter. Hydrochloric acid, we don't have any polyatomic ions that contain chlorine. So that's not as big of a deal. But for this one, it's really important. So the hydro tells me it's binary, so it's hydrogen and sulfur. So it's really important you know when to put the hydro. So as far as our cation, it's hydrogen, because it's an acid. As far as our hydro, that means it's binary, so our anion is S2-. And again, the 2- comes from the periodic table because it's sulfur, so based on where it is. So now to balance that, we're going to balance it just like we would any ionic compound. We need 2 hydrogens for every 1 sulfur, so it balances, H2S. Then we want to put that AQ at the end to represent that it's dissolved in water. And that's the full drawn out name. We can always double check to make sure that our charges do cancel out. It's just like in the ionic compound, we should have a neutral overall charge. Now let's look at carbonic acid. Now carbonic acid doesn't have the hydro, so we know that it's an oxyacid. It's one of the polyatomic ions. So clearly we're starting with H+. Anytime we have acid, that's true. Also notice in the name we don't have to put aqueous. It's just in the formula. Then we have carbonic. There we go. We know it would have come from 8, so that's our CO3 2-. So writing that down, we're going to balance that just like we would. And we need 2 hydrogens in this case to balance, so that's H2CO3. Again, we don't need the parentheses when we only have 1 of that polyatomic ion. And again, we want to put aqueous to represent that it's dissolved in water, forming the acid. And we can always double check our charges to make sure that they do in fact cancel out. Last one, sulfurous acid. Again, there's no hydro, so we know it is a polyatomic ion. So just like before, we're starting with H. That's true for all acid. Us would have started with ITE, so that's SO3 2-. And then we just have to balance it. It won't always come out to H2 and whatever your anion is. It just so happened that these 3 examples all had a 2- charge. That's not always the case. So as you can see, we're going to put aqueous again at the end, and that's the full formula. And we can double check. The last thing that we're going to really get into today, and we're going to finish this up. Now we might not finish the whole chapter on Friday, and our test is going to be on chapter 3 up to where we get. And what we don't cover will be on your next test, because I'm not moving the test. So I won't test you on things I haven't covered. Some people do, I don't do that. So just keep that in mind. Wherever we finish on Friday, that's what I'm testing up to for your test on Monday. Anyway, back to this. Our formula mass. We've talked about our atomic weight of our elements. But what about when we have a compound or an ionic bond or a covalent bond? Well, now we can determine our formula mass. So our mass of our individual molecule or formula unit of our ionic compound. When we're talking about covalently bonded atoms, we call it a molecular formula. When we're talking about ionic compounds, usually it's just formula mass. But you also hear it as molecular weight a lot. So all that is the sum of our masses of our atoms in our compound. Because remember, we talked about the law of conservation of mass. Whatever we have started with, that's what we have to have. So if we have 1 oxygen and 3 hydrogens, our mass is going to be the mass of 1 oxygen plus 3 hydrogens added together. So we have to consider how many of each atom we have as well. And we can, of course, get our atomic mass from the periodic table. And you want to be as clear with your, whatever periodic table I give you, however many decimal places I give you. Remember, those decimal places represent your isotopic amount in nature. So your relative isotopic weight. So it's important you use that correctly. So remember, your whole is the sum of all the parts. you don't have to memorize this formula, but all it's saying is, let's say we have 3 oxygens. We're going to take our atomic mass of our oxygen and multiply it by 3. And then let's say we have however many of another element. We're going to take that amount and multiply it by the mass of that element, and so on until you get the total. Very straightforward. So for example, H2O, that's our water. We have 2 hydrogens. So to get our molecular weight, we would take our hydrogen mass from the periodic table, 1.01, and our oxygen mass, which is 16. We have 2 hydrogens, we have 1 oxygen, so total is going to be 18.02. Fairly straightforward again. You just need to make sure, as long as you have a periodic table, you can figure out the mass of any molecule. If you have the formula in the periodic table or the name in the periodic table, you can figure this out. And again, you don't have to memorize these things from the periodic table, though honestly we'll work with oxygen and nitrogen so much you'll start remembering a lot of them. So they can be calculated from our relative masses of molecules, because remember, if our atomic mass of hydrogen on the periodic table is telling us for every 1.01 grams of hydrogen, that's how we have 1 mole of hydrogen, then we can do the same thing with our atomic mass. So if we look at this, we know that 1 molecule of H2O contains 2 hydrogen atoms and 1 oxygen atom. So we have a relationship with that with our molecular weight and our mass. And that's going to be something we're going to be using a lot. So we know our molar mass is equal to 1 mole or molecule of H2O. So what we can say is, if 1.01 AMU of hydrogen means we have 1.01 grams per mole hydrogen, when we add that up, we get a total of 18.02. That means we have 18.02 grams of water per every mole of water. So just like your grams per mole before, it's still your grams per mole. And just like before, we can use this in a relationship. Because we know, it was so close. Because we know we have 18.02 grams of water for every 1 mole of water. Now remember, that's specific for water. Another molecule is going to have a different amount of grams for every 1 mole of itself. So you have to figure this out for every molecule or every ionic compound. So for example, we have C2H4O2. So we have carbon, hydrogen, and oxygen. From the periodic table, carbon is 12.01 grams per mole. We have 2 of them, so we would multiply that. We have hydrogen. We have 4 of them. So 4 times 1.008, that periodic table is a little bit more specific. Sometimes you'll see 1.01 on some periodic tables. Whatever periodic table I give you, use that one, because that will be in correlation with your multiple choice. And then oxygen is 16.00, so we have 2 of those. So we just add that together, and what that tells us is for every 60.5 grams of C2H4O2, we have 1 mole of C2H4O2. And that gives us our molar mass, or our molecular weight. You'll hear those terms equally. So we can use that, like I said, for relationships. Sorry. I was trying to give you a little bit more time, and it does this really weird thing. All right. Whew. A hint, you don't really have to do the full calculation to figure this out. So just like we could have this relationship between grams and moles of our individual atoms, if we look at our atomic weight, we can do the same with our molecular weight. So we can use this as a relationship in conversions. If I know how many grams of water I have, I can calculate how many moles of water I have. Then I can calculate how many actual molecules I have, or atoms, depending on, typically we use molecules. Now, technically, a mole and a molecule are not necessarily the same thing. It's a part related to our periodic table. But we can do this in calculation. So first off, if I have an amount of grams of PbO2, and I want to know how many moles are in it, I can do that calculation because I'm given a couple of things. I'm given my mass of my lead dioxide. So I have 50 grams. And I can calculate, and here it's given you your atomic mass of lead and oxygen. You don't necessarily need that atomic mass. You can put it in the periodic table, but for our discussion, so you see it there. Also, sometimes once I know and I'm fine that you have this, on later tests I might give you the molar mass just so it doesn't take your time to calculate it. But at this test, I'm going to be testing you on calculating this. So we want our moles of our lead. I don't know how many. Let's see. -2. So it must be +4. So our lead 4 oxide. It's very. So what we have 1 lead and we have 2 oxygens. So we can calculate our molar mass, which is 239.2, and that gives us our relationship of our grams of our molecule with our moles, which is 239.2 grams. So our plan, we know our grams, we can calculate our moles using our relationship. So we want our grams at the bottom. And again, what I like to do, right now it's not as important, but later on, and this is just to remind you, that this is specifically for this compound. This would be different for another compound, so I like to draw this in to remind myself, and later on, this will be important when we are using equations as relationships. So our grams can cancel out, so that goes in the bottom. And remember, your molar mass, your AMU, is grams per mole. So that number is how many grams per 1 mole. Don't mess this up. It's not 239.2 moles per gram. It's grams per mole. I see that mistakenly done all the time. So our grams cancel out, and we're left with our moles. And according to this, we started with 3. So we should have 3 of our significant figures. And since our given amount, we were given less grams than how many grams we have per mole, it makes sense our moles are less than 1. If we had 500 grams, then it would make sense that number would be more than 1, because we know how many grams we have per mole. So we can always rationalize that. Here, we're given the amount of molecules, and we want to figure out, or we want to know how many molecules are in a certain amount of grams of dry ice. Dry ice is just CO2, so don't let this confuse you. It's just CO2 in the solid form. If I gave you dry ice, I would tell you it was CO2, so that's when you should know. If I gave you like some weird name, I'd have to tell you the one. Because right now you don't need to memorize that. So we're given our grams, 10.8 grams of carbon dioxide, and we want to find our molecules. So we can calculate our moles using our periodic table, and then we can convert that to molecules. So first off, our relationship, if we calculate this from the periodic table, we have 1 carbon at 12.01 and 2 oxygens at 16.00. So when you add that together, you have 44.01. Make sure you can do that on your own. So that tells me I have 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. And then I know how to relate my moles to my things. which is, remember, our Avogadro's number, which is 1 mole of whatever our CO2 to 6.022 times 10 to the 23rd molecules. So we just do those calculations. Our grams must go at the bottom so they can cancel out. And then our moles go at the bottom so we can cancel out the left molecules. This comes out to 1.48 times 10 to the 23 molecules of CO2. Note, because this is going to be important for answering that iClicker question that we just went through. Because our grams are in the bottom, the bigger this number, the smaller this number. Because it's at the bottom. So you don't really have to do the full calculation for the iClicker question I showed you. You just need to know the molecular weights. Whichever one has the smallest molecular weight is going to give you the bigger amount of molecules because we're dividing. So we'll look at that in a second. Again, you need to know Avogadro's number. I'm not going to give it to you. And remember, you need to know its relationship, why we know it. And we know it because it tells us for every 1 mole, we have 6.022 times 10 to the 23rd things. We've talked about atoms. It could be footballs, could be molecules as things. Oh, I have one more. Here we're going from molecules to the mass. Again, same thing, just a reverse of what we just did. I didn't realize I still had this one in there. So we're starting with molecules this time of NO2. We want to find our grams. So we're just going to do a reverse of what we did in the example before. So we're starting with our molecules. We can use Avogadro's number to figure out our moles. Once we get our moles, then we have to use our specific molecular weight for that molecule that we can calculate from the periodic table to figure out our amount of grams. So we need our relationships. We know our relationship between mole and our Avogadro's number. So we have that one. And we can calculate our molar mass. We have 1 nitrogen. Looking on the periodic table, it's 14.01 AMU. We have 2 oxygens, 16. And NO2, therefore, is 46.01, which tells us how many grams of NO2 we have per 1 mole. So that's our relationship. Then, of course, we have our relationship between Avogadro's number. So now we're starting with molecules. So our molecules go at the bottom this time. And then those can cancel out. Then our moles can cancel out. Remember, this is 46.01 grams per mole, not 46.01 moles per gram. Don't flip that. That's not true. What's true is it's related to grams per 1 mole. So when we do that calculation, we get 365 grams of NO2. Since it's more than Avogadro's number, it makes sense that we have a large amount of grams. So looking at this one, like I said, the key here is the fact that we're taking our molecule grams, and we're going to divide it by our grams per mole that we calculate from the periodic table. So the question is, which one has our lowest molecular weight that's going to give us our biggest number? Just let me finish this one, guys. Don't make too much noise. Other people are trying to listen. So when we calculate CH4, we see that that's going to be 16.033 AMU. C2H6. Again, you should be able to do these on your own, so pull out your periodic table when you get home and go through them. And if you look at Xe, Xe actually has an atomic mass that is the biggest. It's very dense. So we can see that CH4 has the least amount of grams per 1 mole, so it's going to have the largest number of molecules, because it's going to have the smallest number on the bottom. You can actually calculate the amount of molecules of each of those, and I suggest you do. But since we're starting with 10 for each, that's what we can do, because we started with the same amount. I do suggest you calculate the amount of molecules in each of these, just to have practice. So you guys have a great day. We're going to talk about percent composition on Friday and finish up what's going to be on the test.